Welcome to Soft-Spoken Mysteries. Tonight, we're diving deep into history's most perplexing vanishing acts. Two stories separated by thousands of miles and thousands of years, yet connected by a single, haunting question. How did we lose this? In our first investigation, we'll explore the largest Bronze Age civilization you've never heard of. A sprawling empire that covered more territory than Egypt and Mesopotamia combined. 5 million people living in sophisticated cities with indoor plumbing, standardized weights and measures, and a writing system so complex that after 100 years of study, we still cannot read a single word. The Indus Valley civilization built an empire that rivaled the ancient world's greatest powers, then vanished without explanation, taking their secrets with them. Then we'll turn our attention to a corroded lump of bronze pulled from a Mediterranean shipwreck, an object so impossibly advanced that when scientists first examined it, they thought it must be a hoax. The Antikythera mechanism, an ancient Greek computer with precision gears that tracked the movements of the heavens, technology that wouldn't be matched for 1500 years. But here's what keeps researchers awake at night. If the Greeks could build this, what else did they create that we've lost forever? So settle in, get comfortable, and prepare yourself for a journey into the shadows of forgotten knowledge. These are the stories of civilizations that reached heights we're only beginning to understand, then slipped through the fingers of history. Let's begin. The year is 1875, British India. An archaeologist named Alexander Cunningham is examining a curious artifact brought to him by a local farmer. It's a small stone seal, barely an inch across, carved with strange symbols, and the image of what appears to be a bull. Cunningham publishes a drawing of it, notes it in his records, and moves on to other discoveries. He has no idea what he's holding in his hands. He doesn't know that this tiny seal is a fragment of evidence from one of the world's most sophisticated ancient civilizations. He doesn't know that beneath the soil of northwestern India and Pakistan lie the ruins of massive planned cities, their streets laid out in perfect grids, their homes equipped with bathrooms and drainage systems that wouldn't be matched in Europe for 3,000 years. He doesn't know that this civilization was already ancient when the pyramids were built. That at its height, it may have been home to 5 million people spread across an area larger than Western Europe. And he certainly doesn't know that more than a century later, despite our satellites and ground-penetrating radar, despite our supercomputers and artificial intelligence, we still won't be able to read the words carved into that little stone seal. The Indus Valley civilization emerged around 3300 BCE in the fertile floodplains along the Indus River and its tributaries. What began as small farming communities slowly coalesced into something unprecedented in human history. By 2600 BCE, they had developed into a full-fledged civilization with urban centres that would make ancient Rome look primitive by comparison. The scale is staggering. The Indus civilization eventually covered an area of approximately 1.5 million square kilometres. To put that in perspective, that's bigger than ancient Egypt and Mesopotamia combined. We're talking about a domain that stretched from the mountains of Afghanistan to the coast of the Arabian Sea, from the foothills of the Himalayas deep into what is now central India. But size isn't what makes the Indus Valley civilization remarkable. It's what they built. It's how they lived. Let's start with Mohenjo-daro, one of their greatest cities. When archaeologists began excavating it in the 1920s, they found something that shouldn't exist. The entire city was laid out in a grid pattern. Not the organic, winding streets that characterized most ancient cities. Not the haphazard construction of settlements that grew naturally over centuries. This was urban planning on a scale that suggests centralized authority and sophisticated mathematical understanding. The streets ran north to south and east to west, intersecting at perfect right angles. Main thoroughfares were up to 10 metres wide. Secondary streets were proportionally smaller. The city was divided into clearly defined zones: residential areas, craft workshops, public buildings. Someone had planned this. Someone had surveyed the land, drawn up plans, and executed them with precision. And the construction standards were uniform across the entire civilization. From Harappa in the north to Dholavira in the south, cities followed the same basic principles. Bricks were manufactured in standardized sizes and ratios. The ratio of 2 to 1 to 4, length to height to breadth, was used consistently across hundreds of archaeological sites. This level of standardization suggests not just planning, but a unified system of weights and measures that spanned the entire civilization. But here's what truly sets the Indus people apart from their contemporaries: their sanitation systems. Every major building in Mohenjo-daro had its own bathroom. Not a communal bathhouse, not an outdoor latrine. Individual bathrooms with carefully constructed drainage. Water flowed from private wells through terracotta pipes. Wastewater drained into covered channels that ran beneath the streets, flowing into larger sewers and eventually out of the city. The sophistication is remarkable. The drainage channels were made from precisely fitted bricks. They had inspection holes for maintenance. They were angled perfectly to ensure proper flow. In some places, archaeologists have found settling chambers where solid waste would separate from water. To understand how advanced this was, consider that when archaeologists first discovered these systems, they initially thought they must be from a much later period, because this level of urban sanitation didn't exist anywhere else in the ancient world. Rome wouldn't build comparable systems for another 2,000 years. Medieval European cities wouldn't have anything similar until the 1800s. The citizens of the Indus Valley had toilets and running water, while most of the rest of humanity was still figuring out basic agriculture. But sanitation was just the beginning. The Indus people were master craftsmen. They produced jewellery of stunning delicacy, carnelian beads so perfectly drilled that modern jewellers struggle to replicate them. These beads were tiny, some less than a millimetre in diameter, drilled lengthwise with remarkable precision. The drill holes are perfectly straight, perfectly centred. Even with modern diamond-tipped drill bits and precision equipment, contemporary jewellers find it challenging to match this level of accuracy. How did they do it? We don't know for certain. Some researchers believe they used diamond-tipped drills, taking advantage of India's ancient diamond deposits. Others suggest they developed techniques using copper drills and abrasive powders. Whatever the method, it required extraordinary skill and patience. A single bead might take hours or days to produce, and they weren't making just a few. Archaeological sites have yielded thousands of these beads. This was production on an industrial scale, suggesting specialized workshops, with trained craftsmen passing their techniques through generations. The shell inlays are equally mysterious. Delicate geometric patterns cut from conch shells and mother of pearl, fitted together with gaps measured in fractions of a millimetre. The precision suggests tools we haven't found, techniques we don't understand. Bronze sculptures demonstrate sophisticated lost wax casting methods, with details so fine they capture individual strands of hair and subtle facial expressions. Their metalworking was advanced beyond what we'd expect from a Bronze Age culture. They produced bronze tools and weapons with consistent alloy ratios. They made copper vessels of remarkable thinness. They created gold jewellery using techniques like granulation, where tiny balls of gold are fused to a surface to create decorative patterns. This requires heating the metal to exactly the right temperature. Too hot, and the balls melt into the surface. Too cool, and they won't bond. The Indus craftsmen clearly understood the properties of metals at a sophisticated level. They worked with materials from across the known world. Lapis lazuli from Badakhshan in Afghanistan, over 1,000 kilometers away, turquoise from Persia, gold from Karnataka in southern India. jade from China, tin from Afghanistan or Central Asia, copper from Rajasthan. This wasn't an isolated civilization. They had trade networks that spanned thousands of kilometers across some of the world's most challenging terrain. Consider what that means. Merchants were traveling through mountain passes, across deserts, navigating rivers and coastal waters. They were maintaining trade relationships with distant cultures. They were standardizing quality and measure so that a weight from Mohenjo-daro would be recognized and trusted in Mesopotamia. This required organization, communication, and trust networks that connected dozens or hundreds of cities and settlements. The seals themselves are fascinating artifacts, made from steatite, a soft stone, carved with images and inscriptions, then fired to harden them. Most depict animals: bulls, elephants, tigers, rhinoceros. Some show composite creatures like the famous unicorn seal, which may actually be a bull shown in profile with one horn visible. But what were they for? The most common theory is that they were used to mark ownership or authority. Press the seal into soft clay, and you create an impression, a sort of signature or stamp of authenticity. Merchants might seal shipments to guarantee they hadn't been tampered with. Officials might seal documents or storage containers to assert authority. But here's what's puzzling. We've found over 2,000 different seals, each with unique combinations of symbols and images. If these were personal signifiers like signatures, then we're looking at evidence of 2,000 literate individuals who needed to mark their possessions or authority. That's a significant literacy rate for an ancient civilization. Or perhaps they weren't personal signifiers at all. Perhaps each seal represented a family, a guild, a district. Perhaps the symbols encoded information beyond just identity. Position in a hierarchy. Type of goods. Origin of a shipment. We can't know because we can't read the script. And we know this because Indus seals have been found in Mesopotamia. In the ancient cities of Ur and Lagash, archaeologists have discovered seals bearing the distinctive Indus script and animal motifs. The Mesopotamians even had a name for the Indus region, Meluha. They wrote about Meluhan ships bringing exotic goods, about Meluhan merchants trading in their markets. The two great Bronze Age civilizations were in contact. They were trading partners. The Mesopotamians left written records describing their interactions with these mysterious people from the East. But here's where it gets strange. While the Mesopotamians wrote extensively about Meluha, while they detailed trade goods and diplomatic relations, while they left us thousands of cuneiform tablets describing their dealings with the Indus people themselves left almost nothing. Oh, they had a writing system, a sophisticated one. We've found over 4,000 inscriptions scattered across the civilization's territory, but every single one is short. The average inscription is just 5 symbols long. The longest known inscription, found on a copper plate, contains only 34 characters, 5 symbols, on average, 5. To put that in perspective, the Rosetta Stone contained almost 1,700 lines of text in 3 different scripts. The Mesopotamians left libraries with hundreds of thousands of tablets. The Egyptians covered pyramid walls with hieroglyphics. But the Indus people, who clearly had a complex society that required record-keeping and administration, apparently never wrote anything longer than a few words. Or perhaps they did, and we just haven't found it. Perhaps they wrote on materials that decomposed: palm leaves, cotton cloth, wood. Perhaps buried somewhere beneath the soils of Pakistan, there's an Indus library waiting to be discovered. But right now, all we have are these tiny inscriptions, and after a century of study, we cannot read them. The script consists of approximately 400 distinct signs. Some scholars think it's an alphabet. Others believe it's a syllabary. Some argue it's logographic, with each symbol representing a complete word or concept. There's no consensus. There's not even agreement on whether it represents a single language or multiple languages. Computer scientists have analysed the statistical patterns of the symbols, the frequency distributions, the order in which signs appear. They've compared it to known languages from every family: Dravidian, Indo-European, Austroasiatic, Sino-Tibetan. They've run machine learning algorithms. They've built neural networks. They've tried every analytical tool modern technology can provide, and they've gotten nowhere. Here's the problem. When Jean-François Champollion deciphered Egyptian hieroglyphics, he had the Rosetta Stone, a single artifact with the same text in 3 scripts: hieroglyphics, Demotic Egyptian, and Ancient Greek. By comparing the known Greek with the unknown Egyptian, he could begin to crack the code. The Indus script has no Rosetta Stone. We've never found a bilingual inscription. We've never found the same text written in both Indus script and a language we can read. Without that key, without that comparison, decipherment becomes exponentially more difficult. And the inscriptions are so short that statistical analysis becomes nearly impossible. You can't analyze grammar when your longest sentence is 34 words. You can't identify patterns of syntax when most of your examples are 5 symbols or less. Some researchers have claimed breakthroughs. In 2025, the government of Tamil Nadu in southern India offered a $1 million prize for anyone who could decipher the script. They claimed recent studies showed similarities between Indus symbols and ancient Tamil graffiti. 60% of signs matched, they said, but other scholars were skeptical. Similarities in shape don't necessarily mean similarities in meaning. And without longer texts, without grammar and syntax to analyze, how could anyone prove their interpretation was correct? The script remains undeciphered. Every symbol, every sign, every inscription is a locked door. And behind those doors might be the answer to one of archaeology's greatest mysteries. What happened to the Indus Valley civilization? Because around 1900 BCE, something changed. The great cities began to decline. Construction quality deteriorated. The elaborate drainage systems fell into disrepair. Trade with Mesopotamia ceased. And by 1800 BCE, the major urban centers were abandoned. 5 million people, an empire that had flourished for over 1,000 years, gone. Not destroyed in a dramatic catastrophe, not conquered by invading armies. The archaeological record shows no evidence of mass destruction. No burned cities, no weapons scattered in the streets. Just a slow fade into obscurity, like a light gradually dimming until the room goes dark. But as researchers look more closely, the picture becomes more complex. The decline wasn't uniform. Some cities were abandoned earlier than others. Some saw a transformation rather than an ending. The pattern suggests not a single catastrophic event, but a cascade of problems that eventually undermined the entire system. At Mohenjo-daro, the later levels show increasingly poor construction quality. Houses that once had sophisticated drainage now had crude repairs. New buildings were erected on the ruins of old ones, but with far less care and skill. The city was still inhabited, but the organization that had maintained it for centuries was breaking down. At Harappa, excavations show evidence of flooding in the later periods. The Indus River, always prone to seasonal flooding, may have become more unpredictable. Climate studies suggest increased monsoon variability around this time. Some years might bring devastating floods. Other years, insufficient rain. Agriculture, the foundation of the entire civilization, would have become increasingly unreliable. And here's a detail that troubles archaeologists. Many of the later skeletons found at these sites show signs of malnutrition. Not starvation, but chronic underfeeding. The kind of nutritional stress that comes from food shortages extending over years or decades. The harvests were failing. The trade networks that might bring supplemental food were breaking down. People were hungry. Theories abound, of course. The first and most popular is climate change. Specifically, the drying of the Gagga-Hakra river system. This massive river, now vanished or reduced to seasonal streams, once flowed through the heart of Indus territory. Satellite imagery and ground studies have revealed its ancient channel, a dry riverbed that once supported hundreds of settlements. Dozens of Indus settlements lined its banks. Archaeological surveys have identified over 1,400 sites along its former course. If the river changed course or dried up, those settlements would have lost their water source, their agricultural foundation, their trade route. And geological studies support this. Analysis of ancient river channels shows significant changes in the Indus and Gagahakra systems during the 2nd millennium BCE. The monsoon patterns shifted, rainfall decreased, rivers that had sustained cities for centuries began to fail. Some researchers point to tectonic activity. The region sits on active fault lines. A major earthquake could dam rivers or alter their courses. There's evidence of seismic activity around 1900 BCE. But would that alone explain the civilization-wide collapse? Others suggest environmental degradation. The Indus people needed massive amounts of wood for brick firing, for metalworking, for cooking and heating. Over centuries, they may have deforested large areas. Without tree cover, soil erosion would accelerate. The land's ability to retain water would decrease. Agriculture would become harder, requiring more effort for less return. There's also the salinization problem. When irrigation water evaporates, it leaves behind dissolved salts. Over centuries, this salt buildup can make soil infertile. It's happened to other ancient civilizations. Mesopotamia's agricultural heartland eventually succumbed to salinization. Could the same have happened in the Indus Valley? But here's what's puzzling. People don't just vanish because rivers dry up or soil becomes less productive. They move, they adapt, they migrate to areas with better conditions. And indeed, we see evidence of exactly that. After the decline of the great cities, there's an increase in smaller settlements in the east toward the Ganges plain. In Gujarat and the Kathiawar Peninsula, the population dispersed, shifting to areas with better water access or more reliable rainfall. So why don't we have records of this migration? Why don't we have stories, myths, legends about the fall of the great cities? Every culture preserves memories of significant events. The Greeks remembered Troy, the Hebrews remembered Egypt, the Norse remembered migrations. But the Indus civilization seems to have left no oral tradition, no folk memory, unless they did and we just don't recognize it. Some scholars point to the Vedic texts of ancient India, written in Sanskrit and composed sometime after 1500 BCE. These texts describe the Vedic people as pastoralists and warriors, very different from the urban, trade-focused Indus civilization. For years, historians assumed these were separate cultures. The Aryans, as the Vedic people were called, were thought to be invaders from Central Asia who swept into India after the Indus collapse. But modern genetic studies complicate this picture. Analysis of ancient DNA suggests continuity between Indus populations and later Indian populations. There wasn't a wholesale replacement. The genes persisted. The people didn't disappear. They transformed. Perhaps the Indus civilization didn't end. Perhaps it evolved. Perhaps climate change and ecological pressures caused a shift from large urban centres to smaller, more distributed settlements. Perhaps the writing system was abandoned, not because the culture died, but because the need for complex administrative record-keeping decreased as society reorganised around different principles. Perhaps the descendants of the Indus people are still there, in modern Pakistan and India, carrying forward traditions and knowledge in ways we don't yet recognise, because we can't read their ancestors' writing. But that's speculation. Without written records, without the ability to read the 4,000 inscriptions we've found, we're left with archaeology and educated guesses. And here's what keeps researchers up at night. The Indus script exists. It's there carved into seals and tablets, waiting to be read. The answers might already be in our museums, carefully catalogued and preserved. We might already possess the knowledge of what happened, of who these people were, of what they believed and how they lived. We just can't access it. Imagine having a hard drive full of the most important historical documents ever written, but no way to read the file format. That's where we are with the Indus Valley civilization. The data exists, the information is there, but without the key, without the ability to crack the code, it might as well not exist at all. In January of 2025, Tamil Nadu's Chief Minister M.K. Stalin announced that $1 million prize for deciphering the script. He said, quote, "Archaeologists, Tamil computer software experts, and computer experts across the world have been making efforts to decipher the script, but it remains a mystery even after 100 years. 100 years. Since Cunningham first published that seal in 1875, we've made incredible advances in technology and archaeology. We've deciphered dozens of ancient scripts. We've mapped the human genome. We've sent robots to Mars. We've built quantum computers and artificial intelligence. And we still can't read 5 symbols carved into a stone seal 4,000 years ago. The Indus Valley civilization built one of the ancient world's most sophisticated societies. They had urban planning that wouldn't be matched for millennia. They had trade networks spanning thousands of miles. They had art and craftsmanship of remarkable skill. They had a writing system that implies literacy and record keeping. And then they vanished, leaving behind ruins we're only beginning to excavate and a script we cannot read. Less than 10% of known Indus sites have been excavated. There are hundreds, perhaps thousands, of settlements still buried beneath centuries of soil. Every year brings new discoveries, new sites, new artifacts, new pieces of the puzzle. Somewhere in the Indus Valley, there might be longer texts. There might be a bilingual inscription, an Indus Rosetta Stone. There might be a library or archive that would finally unlock the secrets of this mysterious civilization. Or perhaps the script will yield to computer analysis. Perhaps machine learning will identify patterns human scholars have missed. Perhaps one of the thousands of researchers currently working on the problem will have a breakthrough. But until then, the Indus Valley civilization remains one of history's greatest mysteries. A civilization that rivaled Egypt and Mesopotamia, that built cities more advanced than anything in the ancient world, that flourished for 1,000 years and then faded away, taking their secrets with them. Now let's shift our focus from the Indian subcontinent to the Mediterranean, from a civilization that lasted 1,000 years to a single artifact that survived 2,000, from millions of people to one corroded lump of bronze the size of a shoebox. The year is 1900. Spring. The Mediterranean Sea near the tiny island of Antikythera between Crete and mainland Greece. A group of sponge divers takes shelter from a violent storm. These are professional divers from the island of Symi, using the recently developed diving helmet and suit technology to harvest valuable natural sponges from the seafloor. When the storm subsides, they explore the local waters. One diver, Elias Stadiatis, descends to about 45 meters depth and immediately surfaces, terrified and incoherent, babbling about a heap of dead naked people on the seafloor. His captain thinks he's gotten nitrogen narcosis, the rapture of the deep, hallucinating from breathing compressed air at depth. The captain goes down himself to investigate and discovers that Stadiatis was right. Sort of. The seafloor is littered with ancient Greek statues, bronze sculptures, marble figures. The dead naked people are actually art. The divers have stumbled upon an ancient shipwreck, and it's full of treasures. Over the next several months, the Greek government sponsors a salvage operation. The divers recover an incredible hoard: bronze statues of philosophers and heroes, marble sculptures of extraordinary quality, fine glassware and jewellery, pottery and amphorae, furniture fittings. It's a floating museum that sank 2,000 years ago, and now it's being brought back to the surface piece by piece. One object escapes notice at first. It's just a corroded lump of bronze, about the size of a large dictionary, encrusted with limestone and unrecognisable. The archaeologists catalogue it and move on to more obviously impressive finds, like the bronze ephebe and the marble horse and rider. But several months later, Sitting in storage at the National Archaeological Museum in Athens, the lump dries out and splits apart, and inside are gears, bronze gears the size of coins, with precisely cut teeth, dozens of them, interconnected in complex arrangements, dials with inscriptions in ancient Greek, pointers and scales, and mechanisms that make no sense because gears like this shouldn't exist in the ancient world. The archaeologists are baffled. Initially, some think it must be from a much later period, perhaps something that fell into the wreck site centuries after the ship sank. Because according to everything historians know about ancient Greek technology, they didn't have precision gearwork. They had simple wheels for mills and pulleys. They didn't have clockwork mechanisms and complex gear trains. Those wouldn't be invented for another 1,000 years in medieval cathedral clocks. But as researchers study the object more carefully, the truth becomes unavoidable. The device is ancient. It came from the same shipwreck as the statues and pottery. Based on the other artifacts and the ship's construction, the wreck dates to approximately 60 BCE, during the late Roman Republic, which means the Greeks had built a machine with precision bronze gears 2,000 years ago, a machine that, over the next century of study, would prove to be far more sophisticated than anyone initially imagined. They called it the Antikythera mechanism, after the island near where it was discovered, and it would force historians to completely rewrite their understanding of ancient Greek technology. For the first few decades after its discovery, the mechanism sat in museums, a curiosity that no one fully understood. Various scholars examined it and proposed theories. Maybe it was an astrolabe, maybe it was some kind of navigational instrument, maybe it was a planetarium. But without being able to see inside the corroded mass of bronze, no one could say for certain. Then in 1951, a British historian of science named Derek J. de Solla Price became obsessed with the object. He spent years studying it, using the best technology available at the time. In 1974, he published a comprehensive analysis based on X-ray images of the fragments. And what he revealed was staggering. The Antikythera mechanism was an astronomical calculator, a device designed to predict the positions of the sun, moon, and planets. It had at least 30 gears, and probably more that were now lost. These gears were precisely cut with teeth, about 1 millimeter long. They were arranged in complex trains that performed sophisticated mathematical calculations. The front of the device had dials showing the date on both the Egyptian calendar and the Greek zodiac calendar. It tracked the position of the sun through the zodiac constellations. It showed the phase of the moon. The back had 2 large spiral dials. One tracked the Metonic cycle, a 19-year period after which lunar phases repeat on the same calendar dates. The other tracked the Saros cycle, a period of 223 months used to predict eclipses. You could turn a crank on the side, and the gears would rotate, advancing or rewinding time. You could set it to any date, and it would show you where the celestial bodies would be in the sky. It was a computer, an analog computer made of bronze gears, calculating astronomical positions, using the mathematical knowledge of ancient Greece. Price called it an ancient Greek computer. He described it as the single most technologically sophisticated artifact from antiquity. And he raised a disturbing question. If the Greeks could build this, what else did they build that we've lost? Because the sophistication of the mechanism suggests it wasn't a one-off experiment. It's too refined, too mature. There are no signs of trial and error in its construction. It's a finished product, which implies there were earlier versions, prototypes, a whole tradition of building these devices. And indeed, ancient texts support this. The Roman philosopher Cicero, writing in the 1st century BCE, described a machine built by Archimedes in the 3rd century BCE that could show the motions of the sun, moon, and planets. The engineer Vitruvius mentioned similar devices. The philosopher Pappus of Alexandria stated that Archimedes had written a manuscript on sphere making, though that text is now lost. So the Greeks definitely built astronomical mechanisms. The Antikythera device isn't unique. It's simply the only one that survived. But Price's work was just the beginning. In 2005, an international team brought cutting-edge scanning technology to Athens. They used high-resolution X-ray computed tomography, the same technology used in medical CT scanners, but far more powerful. They created three-dimensional maps of every gear, every inscription, every detail hidden inside the corroded fragments. And they discovered things that made Price's analysis look simplistic. The device had far more gears than Price had found, at least 40, possibly more. The inscriptions were far more extensive, with thousands of tiny Greek letters covering every surface, describing how to use the machine and explaining the astronomical theories behind it. And most remarkably, the gear trains were doing mathematical calculations that seemed impossible for the ancient Greeks. Let me explain why this is significant. The Moon doesn't orbit Earth in a perfect circle. It follows an elliptical path, which means it moves faster when it's closer to Earth and slower when it's farther away. This variation in the Moon's speed is called the first lunar anomaly, and it was known to ancient astronomers from their observations. They could see that the Moon didn't move at a constant speed against the background stars. But predicting exactly where the Moon will be at any given time requires complex mathematics. You need to be able to calculate the position along an elliptical orbit. And that's not simple arithmetic. It requires what we'd now call calculus, or at least sophisticated geometric methods. The equations involve trigonometric functions and what modern astronomers would recognize as Fourier analysis. The Greeks knew the theory. They had developed models of planetary motion using epicycles, circles upon circles, that could approximate elliptical orbits. Hipparchus, the great astronomer of the 2nd century BCE, had calculated the Moon's orbit with remarkable precision. Ptolemy, in the 2nd century CE, would elaborate these models in his Almagest. But actually building a mechanical device that could perform these calculations? That seemed beyond their capabilities, until researchers looked closely at a specific gear train in the mechanism. They found something called a pin and slot mechanism. 2 gears, one mounted slightly off-center relative to the other, connected by a pin that slides in a curved slot. As the gears rotated, the slot caused the output gear to speed up and slow down in exactly the pattern needed to model the Moon's variable motion. It was brilliant, it was elegant, it was a mechanical analogue of elliptical motion, performing continuous calculations without any electronic components or computer programs, just bronze gears and geometric principles. The ancient Greeks had invented a solution to a calculus problem using pure mechanics. And that wasn't all. The inscriptions revealed that the device also tracked planetary motions. Mercury, Venus, Mars, Jupiter, and Saturn. All 5 planets visible to the naked eye. The front inscriptions, carefully decoded from X-ray scans, provided what researchers call the front cover inscription, a user's guide that described planetary cycles and predicted positions. The gear trains that accomplished this are mostly lost now. The front section of the mechanism, where the planetary displays would have been located, is almost entirely missing. We have some gears, some fragments, but not enough to reconstruct the complete system with certainty. However, the instruction manual survives. The tiny Greek letters, requiring magnification to read, explain how the device displayed planetary positions. They describe synodic cycles, the periods between planetary events as seen from Earth. They provide numbers, specific day counts, for each planet's movements. And here's what makes recent research so exciting. In 2021, researchers at University College London published a paper proposing a reconstruction of the lost planetary mechanism. They used all the available evidence, the surviving gear fragments, the inscriptions, the ancient Greek astronomical theories, and mathematical modelling. Their proposed gear train is spectacularly complex, using over 30 gears to calculate the positions of all 5 planets simultaneously. The ingenuity, is remarkable. The Greeks couldn't just calculate planetary periods and build gears with the right number of teeth. Some of the periods involved prime numbers so large that the gears would be too big to fit in the device. Venus, for example, has a highly accurate cycle of 720 synodic periods in 1151 years. But 1151 is prime. You can't factor it. You can't break it down into smaller gears. So the designer found alternative period relations, approximations, that were slightly less accurate but could be expressed as ratios of smaller numbers. For Venus, they used 289 synodic periods in 462 years. These numbers factor nicely. 289 equals 17 times 17, and 462 equals 2 times 3 times 7 times 11. You can build a gear train from factors like that. It's the same challenge NASA engineers face today when designing planetary probes. You need to balance accuracy against practical constraints. The Greek engineer who designed the Antikythera mechanism was solving the same optimization problem ancient astronomers faced, finding the sweet spot between precision and feasibility. Let me put the sophistication of this device in perspective. The next comparable geared mechanism we know of is a Byzantine calendar device from the 6th century CE, about 600 years later. And it's far simpler than the Antikythera mechanism, just a basic geared calendar to help track dates. The first sophisticated astronomical clocks in Europe appeared in the 14th century, devices in cathedral towers that showed the time and the movements of celestial bodies. They were marvels of medieval engineering, celebrated as wonders of their age, and they were still less complex than the Antikythera mechanism. A device built by the Greeks 2,000 years ago contained more gears, more sophisticated gear trains, more accurate astronomical calculations than anything that would be built in Europe for over 1,000 years. The technology existed, it was real, it was functional, and then it vanished. Why? That's the question that haunts historians of technology. The Greeks clearly had the knowledge to build precision-geared mechanisms. They had the mathematics to calculate astronomical cycles. They had the metallurgy to cast bronze gears with millimetre-scale teeth. They had the craftsmanship to assemble dozens of components into a working device. This wasn't theoretical knowledge. This was practical engineering. Someone designed the mechanism. Someone built it. Someone used it, presumably to demonstrate the astronomical principles or to make predictions. And somehow, this entire tradition was lost. Perhaps the knowledge was too specialized. Perhaps only a few workshops or schools possessed the skills to build these devices, and when those institutions disappeared, the knowledge disappeared with them. Perhaps the devices were too expensive to build, requiring rare materials and expert craftsmen, so only wealthy patrons could afford them. When the economic conditions that supported such luxury items changed, production ceased. Perhaps written instructions existed, but were lost when libraries burned or decayed. We know the Library of Alexandria contained hundreds of thousands of texts. We know most of them are gone forever. Perhaps somewhere in that vanished collection was Archimedes' manuscript on sphere making, the instruction manual for building astronomical mechanisms. Or perhaps the tradition didn't vanish. Perhaps it was transmitted east to the Byzantine Empire and then to the Islamic world. Medieval Islamic engineers built sophisticated automata and mechanical devices. The Book of Ingenious Devices, compiled in 9th century Baghdad, describes over 100 mechanical contraptions. Some historians see echoes of Greek knowledge in these Islamic designs. Perhaps the tradition moved east while Europe descended into what we unfortunately call the Dark Ages. Perhaps the Greeks passed their knowledge to the Arabs, who preserved it and elaborated on it, eventually passing it back to medieval Europe, where it would inspire the cathedral clockmakers. But that's speculation. The direct evidence doesn't exist. We have the Antikythera mechanism, this one miraculous survivor from a shipwreck. We have ancient texts mentioning other devices that are now lost. And we have a 1,000-year gap in the archaeological record before comparable technology reappears. It's as if someone invented the airplane in ancient Rome, then humanity forgot about powered flight until the Wright brothers. Let me tell you what keeps researchers awake at night. It's not just that we lost the technology to build the Antikythera mechanism. It's that we lost it so completely that when divers found the corroded device in 1900, scientists initially thought it must be fake or from a later period. The knowledge was so thoroughly erased that when we finally rediscovered physical evidence of Greek gear work, we didn't believe it could be real. Our understanding of ancient technology had degraded to the point where the actual artifacts seemed impossible. What else did we lose? What other technologies did the ancient world possess that left no trace? The Romans had concrete that's more durable than modern concrete. The formula was lost for over 1,000 years. We've only recently figured out how they made it. The Greeks had a military weapon called Greek fire, a liquid that burned on water and couldn't be extinguished. The Byzantine Empire used it to devastating effect in naval warfare. The formula was kept secret, and eventually that secret was lost. To this day, we're not entirely sure what it was. Damascus steel, produced in the Middle East, had properties that modern metallurgists struggle to replicate. The forging technique was lost. Ancient batteries might have existed in Mesopotamia, the so-called Baghdad batteries, though their purpose is debated. Flexible glass allegedly demonstrated to the Roman Emperor Tiberius which could be bent without breaking. The inventor was executed to protect the glass industry, or so the story goes. These are just the technologies we know about because ancient texts mention them, or because we've found mysterious artifacts. How many others vanished completely? How many innovations left no record at all? The Antikythera mechanism proves that our assumptions about ancient capabilities are often wrong, badly wrong. It proves that sophisticated technology can be lost so thoroughly that later civilizations have no memory of it. And it raises a disturbing possibility. What if this keeps happening? What if the arc of technological progress isn't a smooth upward climb, but a series of peaks and valleys? What if we've lost and rediscovered fundamental technologies multiple times throughout history? We like to think of ourselves as the pinnacle of human achievement. We have smartphones and satellites, genetic engineering, and quantum computers. Surely we're more advanced than any previous civilization. But the Antikythera mechanism suggests humility might be appropriate. 2,000 years ago, the Greeks built a computer, a device that performed complex mathematical calculations using mechanical principles. They didn't have electricity or silicon chips, but they accomplished something remarkable nonetheless. And then they lost it. What are we building now that our descendants might lose? What knowledge do we take for granted that could vanish if the right combination of disasters struck? Our technology is largely recorded in digital formats. What happens if power grids fail? If the internet goes down? If we lose the ability to manufacture the hardware needed to read our storage media? Perhaps there's a hard drive somewhere in an abandoned building filled with crucial knowledge, but no one alive knows how to interface with it anymore. Perhaps our civilization's version of the Antikythera mechanism is sitting in an e-waste dump, its secrets locked behind dead batteries and obsolete file formats. The Greeks didn't intend to lose their astronomical mechanisms. The Indus people didn't plan to leave their script undeciphered. These things happened through the accumulation of small losses, the gradual degradation of knowledge, the failure to pass information from one generation to the next. It can happen to us. In fact, it's already happening. We've lost the ability to build certain components of the Saturn V rocket that took us to the moon. Not because the knowledge is impossible, but because the original engineers have died, their expertise not fully documented, the manufacturing processes not preserved in sufficient detail. We've lost programming languages and file formats from just a few decades ago, data that's technically still recorded on magnetic media, but practically inaccessible because no one remembers how to read it. Knowledge is fragile. Technology is fragile. Civilization is fragile. The Antikythera mechanism reminds us of that fragility. It sits in a museum in Athens now, carefully preserved, extensively studied. Researchers continue to analyze it using ever more sophisticated scanning technologies. They continue to build replicas, testing theories about how the lost gears might have functioned. A YouTube channel called ClickSpring has documented the construction of a full replica using only tools and techniques available in ancient Greece. The creator, a professional clockmaker, has spent years carefully machining each component according to the evidence from the original. The project has revealed insights about ancient manufacturing methods, about the skill required to produce such precise gears without modern machine tools. And it has confirmed what researchers suspected. The device worked. It wasn't theoretical. It wasn't ceremonial. It was a functional calculating machine that, when properly built, could predict astronomical positions with impressive accuracy. The Greeks built it. They used it. They lost it. Somewhere in the ancient world. Perhaps in a workshop on the island of Rhodes where the great astronomer Hipparchus studied the heavens. Or perhaps in Syracuse, where Archimedes invented war machines that held off the Roman fleet. There were craftsmen who knew how to build mechanisms like this. They passed their knowledge to apprentices. They wrote instruction manuals. They demonstrated their devices to students and philosophers. And eventually, through some combination of war, economic collapse, changing priorities, and historical accident, that knowledge disappeared. The workshops closed, the texts were lost, the tradition ended. Until a team of sponge divers seeking shelter from a storm happened to explore the waters near Antikythera. Until one of them descended to the seafloor and found a heap of ancient treasures, including one corroded lump of bronze that would prove to be one of history's most significant artifacts. The Antikythera mechanism is evidence of heights we reached and then forgot. It's proof that human ingenuity in the ancient world was more sophisticated than we ever imagined. It's a warning about how completely knowledge can vanish. And it's a challenge. If the Greeks could build this 2,000 years ago with bronze and geometry, what could we build with our modern technology and understanding? What wonders are we capable of that we haven't yet imagined? What knowledge are we preserving for our descendants? And what are we about to lose? Tonight we've explored two mysteries that share a common thread. The Indus Valley civilization built an empire that rivaled the ancient world's greatest powers. They developed sophisticated urban planning, advanced sanitation, extensive trade networks, and a writing system that has defied decipherment for a century. Then they vanished, leaving behind ruins and 4,000 inscriptions we cannot read. The Antikythera mechanism demonstrated that the ancient Greeks possessed technological capabilities far beyond what historians believed possible. They built a computer 2,000 years before the digital age, using bronze gears to calculate the movements of the cosmos. Then that knowledge was lost so completely that when we found physical evidence of it, we initially didn't believe it could be real. Both stories remind us that history is not a straight line from primitive beginnings to sophisticated modernity. Both remind us that civilizations can reach remarkable heights and then fall back into darkness. Both remind us that knowledge is precious and frighteningly easy to lose. The Indus script exists. The information is there, carved into seals and tablets, waiting in museums. But without the key to decipher it, it might as well be random symbols. The Antikythera mechanism exists. We have it, we've studied it, we've scanned it with the most advanced imaging technology available, but the knowledge of how to build it was lost for 15 centuries. What else have we lost? What other wonders did the ancient world create that left no trace? What technologies, what mathematical insights, what engineering marvels vanished because no one wrote them down, or because the texts were destroyed, or because the tradition wasn't passed to the next generation? We'll never know. That's what makes these mysteries so haunting. It's not just what we don't know, it's what we can't know. It's the knowledge that was deliberately recorded, carefully preserved, and then lost anyway. The Indus people left us their words. We just can't read them. The Greeks left us their technology. We just couldn't believe it. And somewhere, buried beneath the soils of Pakistan, or resting on a Mediterranean seafloor, or collecting dust in a museum basement, there might be other artifacts, other inscriptions, other devices that could revolutionize our understanding of the ancient world. If we can recognize them for what they are, if we can figure out how to decode them, if the knowledge hasn't been lost completely. Until then, we're left with fragments, with corroded gears and undeciphered symbols, with questions that have no answers, and mysteries that deepen the more we learn. The Indus Valley civilization disappeared, taking its secrets with it. The tradition of building astronomical mechanisms vanished, leaving only one miraculous survivor. And we're left to wonder, what else did we lose? What other wonders are waiting to be rediscovered? What knowledge will our civilization lose? That's all for tonight's investigation into the shadows of lost civilizations and forgotten technology. Thank you for joining me on this journey into history's greatest vanishing acts. Tomorrow night, we'll explore different mysteries, different stories from the dark corners of the past. Until then, sleep well. And perhaps dream of bronze gears calculating the cosmos, of cities with sophisticated drainage, of knowledge lost and waiting to be found again. This has been Soft Spoken Mysteries. Good night.